Sure, thanks so much. My name is, oh, give me one second. There we go. Yes, so nice to meet everyone. My name is David Malan, and I've been teaching at Harvard Extension School for some 20 years now, and I actually got my start through Harvard Extension. So in fact, if you'll indulge me, I thought I'd rewind those 20 years to a different course altogether that at the time was called Computer Science E-1, and this was in 1999, and it was literally called Introduction to Computers and the Internet. It wasn't computer science, it was computers and the Internet, and it drew a demographic of folks who were generally familiar with computers, might not have been on the internet themselves yet, but we're eager to sort of catch on to what this was all about. This then was where I got my start. It has since evolved into a different course that is still in the course catalog nowadays called Computer Science E1B, which is computer science for business professionals. And in fact, if what you're about to experience today in our hour together feels like maybe a lot, maybe a little bit over your head, that too is fine. The material we'll cover is covered at a slower pace, a gentler and more accessible pace through this particular course here. But if I do rewind back to 1999, this is how we were doing technology back in the day. So we had a teaching fellow, or TF, in the room who was filming classes on VHS tape. Those were then put on hold in the Harvard library, so at least students on campus, if they missed a class or wanted to review it, they could check out literally a videotape from the library. But of course, then came along streaming media, and so I'll say that by shortly thereafter, we started recording lectures too in a format that looked about as good as this. So if you're having trouble seeing what's going on the screen here, I mean, that was the state of the art back in the day. But I bring this up because even though you and I rather take for granted the fact that we're on Zoom right now and there's just this plethora of educational resources online, to me this was completely non-obvious back then. And it wasn't until a student in Computer Science E1 I think emailed me after the first class to say, would you mind posting yesterday's lecture notes online, that it even occurred to me that people would want digital copies of these kinds of assets. And that actually really triggered a whole philosophy for me and a lot of my colleagues, whereby thereafter, pretty much after that first lecture in 1999, we started to put everything online. And indeed, as soon as we had the ability to move away from VHS tapes to, in the year 2000, something that was called Real Video at the time, which was a really small video player that you could play on your Mac or PC, this was now an opportunity to make those same video assets available to folks beyond the library and actually let folks on campus and off engage in the course's material. Indeed, if you focus in on this, like this was, just to make this really clear, this was the state of the art. This was the state of video not too many years ago. And then if we fast forward just a few years, 2004, you might recall that the iPod became a thing. It was just audio initially for what were called MP3 files, music files and the like. And so the next evolution of what we were doing through Harvard Extension was making our class available not just through streaming video, but also offline via podcast, which is a term that most everyone nowadays knows, but was very bleeding edge at the time. And the motivation in 2004 was very simple. I mean, as luxurious as it was to be able to stream a class onto your Mac or PC, the reality was you were rather tethered to that Mac or PC. And certainly 15 years ago, the internet wasn't nearly as omnipresent or bandwidth as good as it is now. So it was actually a value add at the time for students to be able to download even an audio recording of lecture in advance and then bring it with them on their commute to work or the like. Just a year later, the video iPod came out. We started making Computer Science E1 available in video format as well. And then fast forward to 2007, when I took over a class at Harvard College called Computer Science 50, Introduction to Computer Science, that is now offered as of that same year through Harvard Extension School as well. So we have about 100 Extension School students through this class each year. We have about 500 undergraduates through this class each year. And the course is also freely available to anyone online on YouTube and edX and other platforms as open courseware, so to speak, where it's a very, very large audience as well. So what is nicknamed Computer Science E-50 is more colloquially known here as CS50. And so over the next like 15, 20 minutes maximally, just wanted to give you a taste of Computer Science E-50, aka CS50, and thereafter take any and all questions about this or material or extension school more generally. Feel free to chime in with a virtual hand or via the chat window at any point if you have questions. But for now, let me just give you a definition of like what computer science is. And if you were to take a class like Computer Science E-50 or that other class, Computer Science E-1B, what is it you would get a taste of? Well, this is kind of the simplest way to think about computer science. It's really about problem solving. And if we try to draw problem solving in the abstract, it really is this notion of an input, like a problem to solve, an output therefrom, which is like the solution that we want. And then somewhere in here is the proverbial black box, where all of the intellectually interesting stuff presumably happens. But let's consider how we can first represent those inputs and outputs. Indeed, this is what we would do on the first day of the class like this, is consider how we can universally represent these inputs and outputs in a way that any computer, and certainly any computer scientist, can understand. But let me motivate this with a question, if you're comfy chiming in the chat. With just one human hand, how high can you count? How high can you count? Hopefully a softball question, just to warm things up here. But in the chat, if you might answer this, with one human hand, how high can you count? Leonardo proposes 5. I see 5 for Mariano. Everyone else is being a little timid, perhaps. Andrea, 5 as well. So pretty universally 5, 6, Mariano. Jermaine notes 0 to 5. I like that as well. I'm going to say, though, that all of you are wrong. OK, so Michael can keep counting, so infinite, but not if you're trying to uniquely hold up those fingers, I would say. So Vito is actually the most correct. As many as 32, technically 31 if we start counting at 0. Now, why is that? Well, if you consider your human hand, well, this is how you might represent 1, 2, 3, 4, 5. And of course, that's why all of us were saying 5 from the get-go. But what if we take into account not just the number of fingers that are up, but the pattern of fingers that are up? And let me propose that maybe this is still 0, maybe this is 1, but maybe this is 2. And maybe this is now 3. And this is often offensive. This is now 4. This is now 5. This is 6. And this is 7. And that's about as high as I can physically count before it gets a little painful. But theoretically, I should be able to continue to permute my fingers in these various ways in order to count as high as 31, giving me, therefore, 32 possibilities from 0 all the way up through 31. So this actually is a hint of what we all kind of probably generally know computer speak, which is binary. We all probably generally know, even if you're not a computer person, that computers only understand zeros and ones. The so-called binary system, bi implying 2, insofar as there's 2 digits, 0 and 1 by convention. So where can we see this, though, in a more electronic context? Well, let's start here very simply with a single light bulb. But light bulbs are nice because they sort of represent a device that's either on or off. And a computer, for instance, has millions of tiny little light bulbs inside of them, or technically switches inside of them. And those switches are called transistors. And because computers are powered by electricity, the computer can turn these switches on or off in order to represent the number 1 if it's on or 0 if it's off. So this single light bulb here that has no power on it might be representing a 0. This now might be representing a 1. But if you want to count higher than 0 and 1, we're going to need more light bulbs, more switches, more transistors. So if I give us 3 light bulbs, all of them are currently off, I'll stipulate that this represents 0. If a computer puts all 3 switches off, that's how it would store the number 0. If it wants to turn on 1 light bulb, that's how it might represent 1. This could be how it represents 2, and this could be how it represents 3, much like my fingers the first time around. But I've kind of painted myself in a corner by just using all of the light bulbs together without really considering the order in which I'm switching them on. So I can actually count higher than 3 with 3 light bulbs. I can actually count as high as 7. 7 is actually the max. So where do I get that? Well, let me start over with 3 light bulbs that are off. Let me turn on the first one, and I'll claim that is how a computer represents 1, by doing off, off, on. This is how a computer would represent 2, off, on, off. And that's reminiscent of my finger, just my pointer being up before, where I claimed this was now going to be the number 2 instead of this with 2 actual fingers. Now it gets a little non-obvious, but let me throw another switch. This is how a computer would represent 3, off, on. This is how a computer would represent 4, and now 5, and now 6, and now 7. And this is equivalent to my 3 fingers being up earlier, which I claimed too was 7, at which point it was starting to get painful. Now, these patterns might look completely arbitrary or non-obvious, but it turns out they're completely familiar to you, even if you haven't thought about it this way for quite a number of years. So for instance, on the screen here is what is obviously the number 123. But let me push a little harder and rewind us to grade school. Why is this the number 123? Really, there's just like 3 glyphs or symbols on the screen that you could draw with a typewriter or a paper pencil. It's 3 symbols, like a stroke representing a 1, a curly stroke representing a 2, and then a doubly curly stroke representing a 3. But you and I immediately infer that that is, of course, the number 123 when all 3 of those symbols are together. But why is that? Well, back in grade school, you might recall that the rightmost digit is in the so-called ones place, or ones column. The next digit is in the tens place. The next one's in the hundreds place. And so even though none of us actually do this arithmetic explicitly, you're intuitively doing essentially this in your head. Well, 100 times 1 plus 10 times 2 plus 1 times 3 gives me, of course, 100. Plus 20 plus 3, or 123. So we go from this pattern of symbols, a 1, a 2, and a 3, but if we take into account the order in which those symbols appear, we ascribe more mathematical meaning to them. So this, recall, is how we might represent 3 digits, the 1, the tens, the hundreds place. But it turns out we can be a little more clever here, and we can work in the notion of decimal more explicitly. Decimal, which is the number system you and I use in the real world, 0 through 9, has dec as its prefix, dec implying 10, because in the real world, most of us use 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, which is 10 total digits. So where do these columns come from? This 1, this 10, this 100? Well, it comes from using a base of 10, and then powers of 0, 1, and 2, which of course is the same, 1, 10, and 100. So if I instead take away some of those digits from you and say, you're not going to use decimal anymore as we humans do, but you're going to use binary like computers do, all we need really do is change the base in this math to be 2, because we have 2 possible digits, 0 and 1, instead of 0 through 9. And if I multiply this out, of course, that gives me a 1's column, a 2's column, and a 4's column. And so now, even though the patterns might not be super obvious, it should now make more sense mathematically when we bring back the light bulbs. Although, let's move away from an analog world of physical devices like light bulbs and use a digital world now of literally zeros and ones, where a 0 is off and a 1 is on. And here then, I claim, is how a computer would represent the number you and I know as 0. Why? Because it's 4 times 0 plus 2 times 0 plus 1 times 0, which of course is 0. We don't even need this many digits. I could get away with just a single digit if I so choose here, just like in the real world. But here now is how a computer represents 1. As 0, 0, 1, because there's a 1 in the ones place. Here is how a computer represents 2. 0, 1, 0. That is to say, off, on, off, as before. Here's how the computer represents 3. Why? Well, it's got a 1 in the twos place, plus a 1 in the ones place. There is our 3. And here is where the pattern sort of changed with all of those light bulbs. 1, 0, 0, that is to say, on, off, off, gives me the number we know as 4, because there's a 1 in the 4's place. This is then 5. This is then 6. And here come the 3 fingers again. This then is 7. And so suppose I now wanted to count as high as 8 in the binary system. How could I do it? Feel free to chime into the chat or with a virtual hand. How could I represent the number we humans know as 8 in binary? Yeah, so Parker proposes add another bit. We would need to have a 4th bit in place here so that I can actually now count as high as 1, 0, 0, 0. So I'm taking care to say 1, 0, 0, 0. This is not 1,000. 1,000 is an artifact of our decimal world. This is just 1, 0, 0, 0. But it happens to represent now the number you and I know as 8. So that's sort of it for binary. Let me pause there and see if we have any questions. You now know how to speak binary, and even though it might not be fun arithmetically, I could now give you any number in the world, and I bet with enough time, maybe paper pencil, you could figure out what the pattern of zeros and ones is just by using that same process. All right. So Mohammed's kind of jumping the gun. What is the letter A? Well, let me actually take one step back and ask the group a question. If this is how computers represent numbers, how do computers represent letters? Well, if the only thing underneath the hood of a computer is millions of these little switches called transistors that can be on and off, that therefore can represent numbers, that's the only alphabet we have as a computer, is numbers in some form. Technically, it's zeros and ones, but you can think of it as decimal numbers, depending on the pattern you've arranged. So yes, Mohammed's actually right in the chat that the way computers represent the capital letter A is by storing in some number of transistors the number we know in decimal as 65. And this is an instance of what's generally known as Unicode. And what Unicode, which is a convention used by computers globally, is they standardize that this is the pattern of zeros and ones that would be stored in a computer's memory using a bunch of little transistors or such to turn electricity on and off to represent the letter A, which again is the number 65. So bit of quick math here. This is the ones place, twos place, fours, eights, 16, 32, 64s place, 128th place. So how do we get 65? Well, this one is, per my louder voice, in the 64s column. This one is in the ones column. So 64 plus 1 gives us 65. So literally, if you were to type a capital letter A on your phone or an email and hit send, what's essentially being sent through the airwaves in some form is the pattern off, on, off, 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 on, thereby sending a capital letter A, aka the number we know as decimal 65. So this is indeed Unicode, and it's a system humans came up with in agreement some years ago that really all systems in the world, for the most part, have adopted. And here's a really big cheat sheet with all possible mappings for English letters of the alphabet. So for instance, here's the chart, and you see that the number 65 is capital A. And wonderfully conveniently, capital B is 66, capital C is 67, 68, 69, and so forth. And then a little farther over here, lowercase a is 97, lowercase b is 98, and so forth. And then there's some punctuation symbols and some weirder things over here. So it turns out that computers by convention use 7, maybe 8 bits, otherwise known as 1 byte. You've all heard and used the term byte in some form, maybe megabyte or gigabyte or something like that. But a byte is just 8 bits, because 8 bits, frankly, is just more useful than 1 bit, because you can count much higher with 8 bits. Indeed, you can represent all of these letters of the alphabet. So if I were to receive then a message from someone, for instance, focusing on just these letters here, which was this. Well, I won't make you do the math during our time together here. Let me just stipulate that this pattern of 3 bytes, so 3 sets of 8 bits, happens to convert to 72, 73, 33. Given that, 72, 73, 33, what message? Mohammed's on top of it again. What message is this? Well, it's the message hi. And the third letter there is a little non-obvious. Here's how we get the H. H is 72. I is 73. And if I actually go backwards, if I look for the exclamation point, there's the 33 over here among all of the punctuation. So indeed, if you were to send a text message containing this pattern of bits, that is to say this pattern of decimal digits, you'd really be sending the message HI and then an exclamation point, because that is how computers have standardized how to send those messages. But there's other types of messages that you and I are very much in the habit of sending nowadays, dare say every day. In fact, does anyone want to guess, besides Mohammed, what character or number this pattern of zeros and ones represents? You could do out the math here, but it'd be a bit annoying. Parker's on the right track. It indeed represents an emoji. In fact, I'll make it a little easier, perhaps. This actually is the number 4,336. Let's see. Let's do the math. 4,036,009. Sorry. 4,036,991,106. I should add commas next time. This is not a duck. It's close to a smiley face. As Andrew notes too, this is, according to last year's statistics, the most popular emoji that you and I and humans around the world are in the habit of sending. So even though this is a picture, you're not actually sending an image per se, like a photograph or a GIF or something like that. You're really just sending a single Unicode character, but your Mac, your PC, your phone has fonts in it that displays certain patterns of zeros and ones when they fall into this Unicode system as these emoji, these pictures that some company has drafted. And in fact, this is why on an iPhone, this face of tears of joy looks like this. But notice the subtle difference on Google, on Android. That same emoji will look a little bit different. And that's because reasonable people can disagree as to the interpretation of face with tears of joy. And so companies, Facebook, Meta, others more generally, have different artists' implementations of these same characters. So it's not embedded in the font per se, as Mariano asks. Rather, there's just a font installed on your Mac, your PC, or your phone that when it sees the pattern of zeros and ones, like that 4 billion value a moment ago, it grabs this image and displays it instead of the capital letter A or B or the like. But let's fast forward. If we now stipulate that, OK, computers can store not only zeros and ones, but they can represent numbers as high as we want using decimal, using more and more bits, and they can clearly represent letters and just characters more generally, be it an emoji or otherwise, how do computers go about representing colors? Well, here, too, the only alphabet we have access to is those zeros and ones. So the only way we can represent colors is by coming up with patterns of zeros and ones that represent them. And many computers use this system, some amount of red, some amount of green, some amount of blue, and they combine it together to give us really any color of the rainbow, if you will. So for instance, oh, spoiler. So for instance, if I were to want to represent the number, the color red, I would represent 3 numbers, some amount of red, some amount of green, some amount of blue. And for today's purposes, I'll just stipulate that the highest you can count when storing colors is from 0 to 255. So if you wanted to represent the color red in a computer, you would store the number 255 and then 0 and then 0 because you want a lot of red, no green, no blue. By contrast, if you wanted to store the color blue, you would do 0, 0, 255, because that would give you no red, no green, but a lot of blue. And if any of you have ever used Photoshop or some graphics program, or if you've made web pages before, you might have used color codes that indeed represent red, green, blue, and everything in between. That's all this same system is. Humans have come up with a system that allow you to store colors by just using numbers. Now, if everything though is just numbers, how does the computer know whether to show you red or green or blue or the capital A or just actual numbers like decimal numbers? Well, it depends on the context, long story short. If you open up some pattern of zeros and ones in Excel, it's probably going to show you numbers because that's the point of Excel. If you open that same pattern of zeros and ones in Photoshop, you're probably going to see colors or some kind of image and anything in between. Now, technically, once you're a programmer, it's really the programmer that tells the computer how to treat these patterns of zeros and ones as a character, a number, an image, or something else. But contextually, it just depends on what program you're using at the end of the day to view them. Music is the same thing. Might be a little non-obvious, but if you're at all a musician, you might know there's musical notes like A, B, C, D, and so forth, maybe sharps, maybe flats. We could just come up with some system that represents each of those notes or pitches using a specific number. Now, that alone is not enough for music, probably. We might want to keep track of the loudness of a note, so the physical equivalent of how hard someone has hit the key on the piano, or maybe how long they've held the key, the duration. So to represent music, you might store the note as a number, the duration as a number, and the loudness as a number. So just like colors, 3 numbers as well. And I saw someone unmute themselves a moment ago. Was there a question or comment? Perhaps just an accidental click. And so let me just stipulate that we can represent everything else, including video, using zeros and ones. Why? Well, what's a video? A video is really just a sequence of images that are changing so quickly that it looks like motion, hence the historical term motion pictures. But an image is just a grid horizontally and vertically of dots. Each of those dots is a color. So videos are really images, but images are really colors. And so we already have a system for storing every dot that's red, green, or blue, or anything in between, for videos and images alike. But that's not it all that remains. And in our final moments here before we transition to Q&A, let's consider what's inside now of this black box. And this is really where you spend most of a course in computer science and programming, exploring this black box and understanding how you can write code, how you can solve problems once we have all agreed on how to represent those inputs and outputs. And indeed, in the computer world, we all agreed years ago to use binary in this way. Well, what's an algorithm? Well, an algorithm is really just step-by-step instructions for solving some problem. And that is the secret sauce that's inside of this black box. Algorithms are what you can implement on paper, pencil, like telling someone step-by-step how to do something. In code is the equivalent for computers of an algorithm. A programmer writes code to translate step-by-step instructions into language the computer might understand. And so the algorithm we use in computer science E-50, and as well as in E-1B for that matter, is this. This is a little dated, the technology I have in my physical hand. You might know it nowadays more like this icon here on your Contacts app. But indeed, in your Contacts on your iPhone or Android device, you've got a whole bunch of names and numbers, probably sorted by first name or by last name. And so that invites the question, how do you, or really how does the computer find someone in that phone book or in the Contacts app? Well, you could, in the physical world, very naively go to the first page and just start looking for someone. If I'm looking for John Harvard, last name starting with H, I could just go one page at a time, looking on each page for John Harvard. And if and when I find John Harvard, I can make the call. So this is an algorithm. It's indeed step-by-step, one page at a time. But is it correct? Well, it is correct. It's just kind of naive, kind of foolish, because it's so darn slow. If there's 1,000 pages in this phone book and the person I'm looking for is like toward the end, it might take me like as many as 1,000 pages to find John Harvard or anyone else. So what could I do instead? Andra knows what to expect. I could do it 2 at a time. 2, 4, 6, 8, 10, 12. So this is an alternative algorithm that certainly sounds faster, and it is faster, but is it correct? Well, if you're careful with this one, it might, yes, get you there twice as fast, but I might get unlucky, and John Harvard or someone might be sandwiched between 2 pages. So maybe once I get to the I section, I have to amend my algorithm to at least double back 1 page to make sure I didn't miss John Harvard unluckily between 2 pages. So that algorithm is twice as fast plus 1 more step just to be safe. So to put this into perspective, if the phone book started with 1,000 pages, the first algorithm might take 1,000 steps to get all the way through it. The second algorithm, much better, 500 steps, because we're doing 2 pages at a time. But back in the day, if you use this technology, and this is actually what your phone is doing virtually, you probably opened up the phone book roughly to the middle, assuming there's no cheat sheet on the edge that tells you which letter is where. You go roughly into the middle, and like me, you're probably in the M section, which is too far. And so what we do in Computer Science E-50 is very dramatically tear the problem in half, throw half of this problem away, leaving us now with a problem that only has 500 pages left, from 1,000 to 500. And then I do it roughly again. Same algorithm. I go to the middle, and now, oh, I've gone a little too far to the left. I'm in the E section. So unfortunately, the whole thing fell apart. But I would, again, metaphorically tear the problem in half, throw the left half away, and now I'm left with 250 pages. And again, 125. Repeat, 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 until I'm eventually left with hopefully just 1 final page. Downside, of course, is I can only do this demonstration once per phone book. And fun fact, it's getting really hard to find phone books. But what your phone is actually doing nowadays is exactly that algorithm. It tends to be called binary search, by implying 2 again, because you're dividing the problem in half, in half, in half. And to put that one into perspective, if this phone book started with 1,000 pages, the first algorithm might take 1,000 steps. The second algorithm might take 500 steps. The third algorithm might take, do some math, 10 steps maximally. Because even if it's 1,000 pages, and you can try this at home, the most times you can tear 1,000 pages in half is roughly 10 times, give or take 1 based on how you round and based on the total number of pages precisely. That's powerful. You can now solve problems so much more effectively by being a little more creative, drawing some inspiration from the familiar real world, and once you have the skills, translate it thereafter to code. So for all that and more, please feel welcome to join us this coming summer, fall, or next spring in Computer Science E-50 itself, aka CS50. If you'd like a lighter introduction that's a little more business world and managerial focused, feel free to join us in Computer Science E1B. And then, if this is alternatively of interest, I started teaching this past year a new course through Extension called Cybersecurity on Intrusion, Hacking, and Detection. So whether you're a technical or non-technical person, if you'd like to better understand the threats to you personally and professionally nowadays, you might find that class of interest as well. And through Danielle, I'm happy to share these slides after so you can reference all of the same URLs. But happy to take any and all questions. Thanks so much for joining us today, and perhaps next term. I see David in the chat has a question. If there was a time when you struggled to learn computer science or programming concept, did you have an effective method to address the fear of failure in school or feelings of being an imposter in a professional environment? Okay, so that escalated quickly. And I don't think I have a method as much as of a mindset. Like that concern is so darn omnipresent, honestly, not just among Harvard Extension School students, but among Harvard College students, and probably among students more generally, who tend to approach all too many subjects with a bit of fear, a bit of uncertainty. And case in point, I still remember when I was in graduate school, so presumably I'd already been doing okay in school if I made my way to graduate school in a PhD program, and I still remember going to one professor's office hours in particular, and I would say half the time, after spending 10, 20 minutes with the fellow, super sweet, super nice, super helpful, super smart, but almost like too smart for his own good, because I would walk out of the office hours nodding, thank you so much, yes, I get it, and no, I didn't get it, because I didn't want to look like an idiot in front of the professor. So all I can perhaps offer is empathy, and I would encourage you to find whatever way works for you personally to just kind of accept that is the fact. Get comfortable being uncomfortable, because you are not alone. And in fact, the Extension School has a good subreddit on reddit.com, if familiar, where I've seen this very topic come up. So I think if you ask or search there, you'll see very similar sentiments. So you're in good company. And Andrew, my colleague here, can you scroll back up in the chat just so I can see some of the earlier questions if you can? But feel free to raise a hand virtually and ask audibly. I don't have control of the chat window here. Yeah, Andra, if I'm saying that right?
Yes, thank you for your time. It's an honor.
Sure.
At this point of your career, how do you keep updated on, or I guess throughout your career, how do you keep updated on what's new? And I mean, things, as you demonstrated, go fast in this field. So
Yeah.
what's your strategy during the week, I suppose?
Yeah, honestly, it's just a lot of reading. And, you know, a lot of the time I feel like I'm wasting time because I feel like I probably shouldn't keep scrolling through this feed or keep impulsively checking these various websites. But I do find there to be a lot of good technical communities on reddit.com, where I mentioned the Extension School subreddit earlier. Like there's one called Learn Programming, and there's just a lot if you search for topics that might be of interest to you. Another popular one is called Hacker News. It's easiest to Google this, but if you go to news.ycombinator.com, which is a venture capital fund, that too tends to be where a lot of geeky people post technology news pretty much throughout the day. Those are honestly two of the biggest nowadays. And I also just kind of keep tabs on like Google News, which surfaces more layperson-like explanations. But those first two resources, Reddit and Hacker News, tend to be more technical and juicy, I would say. And Callie, if I'm saying this right in the chat, wrote, if speaking to an audience of non-STEM-minded professionals, what would you say is the most important thing for humanity-minded folks to understand about coding? I want my education and sociology crew to understand the value of minimal coding understanding. A really good question. And I would say that's actually largely the intent of our E1B class, which is not a programming class. We spend 2 weeks only on programming, and we spend 2 weeks on cloud, and we spend 2 weeks on what the internet is, and we spend 2 weeks on other topics as well. And I think it's valuable for everyone to have a taste of programming. And this can be in a few different ways. Like within CS50 and that other class, we actually use a graphical language at the start called Scratch, which is designed for kids like 6 years old and up, built by MIT's Media Lab. But what's really nice about it is it has this very user-friendly interface for dragging and dropping puzzle pieces and making characters move up, down, left, right on the screen, and much more. But each of those puzzle pieces represents very industry standard programming concepts in a certain category of programming, things called loops and conditionals and functions and variables and the like. So even with this very toy-like environment, can you really get a good mental model for what programming is? Perhaps more deep than that would be, you know, a day's workshop on a language like Python, which is a very popular language nowadays. And you can only get so much done. You can only learn so much in just a day. But I think it's the hands-on aspect that's particularly valuable there. So I think finding a resource that you can take asynchronously at your own pace, or coordinating like a day-long workshop or a weekend type thing, is probably the right taste for more business-minded folks to just have a better sense of what their colleagues in the engineering department are actually doing. Anastasia asks,
oh,
sorry. Danielle,
we
please.
do have one coming from the Q&A box,
Sure.
which is from Michael, and he just asked, are there a few characters in between capital and lowercase letters so they align horizontally on the cheat sheet chart, or is that just a coincidence?
No, that is very much deliberate. If I go back to our chart here, you will actually see that, again, capital A is 65, and over here, lowercase a is 97. And if you do the math, that's 32 away from the other. And that pattern continues, 32 away for all of the letters of the English alphabet. And this is getting low-level geeky, but that means you can change a character from uppercase to lowercase by just changing the 1 to a 0 or a 0 to a 1 in the 30 seconds place of the binary representation thereof. So it's kind of a neat trick to do it very efficiently. Good question. And Anastasia had asked, what developments in the CS field are you most excited about? So it's hard not to mention AI nowadays. I will say that I think AI is very exciting educationally. And indeed, within Computer Science E-50, we very much steered into it. We don't allow students in the class right now to use off-the-shelf tools like ChatGPT, which just tend to be too helpful, outright handing you answers to problems as opposed to sort of guiding you toward them like a good teacher. So we have our own CS50 duck, so to speak. And if you want to check this out, you can go to cs50.ai. You just need a free GitHub account if you're familiar with that. But that will let you log in and have a ChatGPT-like interface, but that is tailored specifically to CS50 and introductory computer science content in particular. So AI, therefore, is very interesting now. I will say my colleagues and I do have an Apple Vision Pro, which is fun. It feels like very much version 0.1 of a technology that's surely going to get better and better in the coming years. Personally, I don't find the virtual clicking on buttons and icons all that compelling, but there is this fantastic dinosaur game or simulation that Apple shipped with the device, which is just mind-blowing. It really does take virtual reality to the next level, even beyond some of the headsets of yesteryear. So there's something very interesting and immersive about that. And if I had to guess, honestly, this very two-dimensional Zoom meeting we're having, and if you see me turning my head, it's because I have a few TV screens in front of me. I mean, this will seem very dated soon, I do think. Once the technology is not annoying and painful to wear for very long, I do think we'll pretty quickly get to the point where we'll feel like we are in the same room as someone, even if they are halfway across the world. So to tie that into education, I actually think, albeit in a higher tier experience, I do think that's going to make it a lot more interesting, a lot more engaging to do things like this in outright classes of just a few years from now. Yeah, David.
Would you recommend learning on a Linux computer for computer science?
It's a good question, only if you are already a Linux person. Otherwise, I think you're probably adding undue complexity when the whole field itself is going to be new to you. I use a Mac still. A Mac is actually kind of a nice compromise because it comes with a Unix-like interface built in. Windows is getting better at that, but it's not quite as turnkey. You have to install some annoying additional software. So Mac is sort of the most friendly way to do it, but I wouldn't rush into installing Linux before your first CS class.
Thank you.
Sure. Oh, Andrew asked in the chat, what are your thoughts on hackathons, but for someone who has just started a data science ALM? So hackathons seem fun. For those unfamiliar, a hackathon is generally a multi-hour event where a bunch of geeky people or aspiring geeks get together and like write code together. And they have different purposes. Within Computer Science E-50 at the end of the semester, we have a CS50 hackathon to which we invite all students if they're local to Cambridge. And it's really a 12-hour opportunity to work on their final projects for the class in a fun, social, collaborative environment. In industry, it's very common for companies to maybe take a Thursday evening or a weekend and host an optional hackathon for their staff, the intent of which is for them not to work on their day job per se, but just build something cool that's somehow connected to the company. And supposedly, rumor has it that back in the day when Facebook first rolled out tagging of faces, where it could detect eyes, nose, mouths, and therefore recognize faces, that apparently grew out of a hackathon project. It wasn't driven by the business folks. It was driven by the engineers in that case. So that's the incentive for a lot of companies to sort of just let people play in this way. But another type of hackathon that's very common in the real world is for companies or organizations to host hackathons. This just bring like-minded people together. Or if they've got some fancy new service or API, as they tend to be called, that they want people to try writing programs for, they sort of bring people together. They're often competitive with prizes for the best application. They're just a lot of fun. So to your question, Andra, what are my thoughts on hackathons? If there's one near you and it sounds interesting, by all means, go to it. Personally, I've never enjoyed competitive programming, which those are to some extent, but it's not quite a race that outright programming competitions are. Mariano?
Hi, so I have a question. I wanted to know what is your opinion on where all the technical careers on engineering, cybersecurity will go with all these advances that AI is coming with? Because I mean, for example, I was putting in the chat like some messages ago that, for example, yesterday was released the first AI software engineer that basically does almost everything. It's not as perfect as a human yet, but way better than ChatGPT 4 and so on. So I wanted to know what's your opinion on this? Like, what are we going with I mean, the people who is in the field?
Yeah, definitely a frequently asked question of late. I think that in the near term, at least, if not medium term, I think AI is just going to generally, make us humans much more productive. And it's really going to amplify the impact that an individual programmer or engineer can have. And I say this after having chatted with and essentially interviewed bunches of friends in industry over the past few months in answer to this FAQ. And a buddy of mine made comments that really resonated with me the most. He invited me to consider within a typical company or organization just how many feature requests there are, maybe from the business folks to the technical folks, how many bug reports there are, like how many mistakes there are in the software that people have reported. And the reality is that most companies, most organizations have a much longer to-do list than they will ever get through, a much longer bug report list than they will ever get through. And so I think right now what's very exciting is that AI can very well speed up the process via which humans can tackle those features and bug fixes alike. AI sometimes can fix them for us and even bite off some of those features. So I think the productivity or the impact of an individual human in the near term is going to and is already being increased. I think the world is only getting more technical. There's so many companies out there, particularly internationally, that don't have websites, that don't have technology stacks. And so there's a lot of opportunity to apply technology. So honestly, I don't see AI putting humans out of business anytime soon. In fact, I think it's going to eliminate a lot of the drudge work and a lot of the work that humans never really enjoyed or prioritized. Longer term, I do think you're more likely to see a world in which an actual programmer, even someone with my technical background, will become more like a product manager, where I tell the AI, I tell the computer what to build for me, but I have enough instincts and enough technical sense to know what to ask, how to fix things, how to guide it properly. But you'll be more like steering a ship as opposed to building it, so to speak, yourself. And I think that is great because that's what happens anyway in industry. When you have a team of colleagues and you move into management, you're asking the other humans to do it. All the better if it's software that's doing it instead. Aaron, over to you.
Yeah, I had recently taken one of the Python classes online with some coworkers and loved that it was free. What motivated you, like, to make it free for everybody? And thank you for doing so, by the way. It was awesome.
Sure. Yeah, that was one of the big turning points in 2007 when I took over that other course, and before that we started making everything freely available. Honestly, I just think it's the right thing to do without sounding trite. I think that universities like Harvard are fortunate to have the resources that we do. It really doesn't cost us anything to make these resources freely available. It's only a good thing to have a more educated citizenry. So I think we just all benefit from that. And I do wish more courses at Harvard and more institutions were doing the same. Other questions? Kevin asks, do you think AI will usher in code-free development? Yes, absolutely. I think to my comment about product managers earlier, yes. And there are already, even before AI, no-code initiatives, so to speak, whereby Scratch, in some sense, is kind of a no-code environment, though it's a little closer to code because you are still using the same building blocks. But there's a lot of software that's tailored toward more business types where it's just logic. So at the end of the day, you still have to be a pretty smart person. And you have to understand logical flow. And if you have any Internet of Things devices or any smart home devices, a lot of that stuff has you implementing conditionals, like if the temperature is this, then turn the thermostat to that, and so forth. And so we're already seeing no code just in the form of more user-friendly interfaces. So yes, I think you'll just see more and more of that over time. And let's see. Andrew, about hackathons specifically, not offhand, honestly, but I think if you Google your city name or some nearby big city and hackathon, you might see some things come up. And certainly nowadays, there might very well be Zoom-based and the like hackathons as well. Let's see. Anastasia asks, is sustainability something you factor into your new curriculum? In a digital transformation class, we learned that Python is one of the least energy efficient languages versus C. Yes, so I think that's overemphasized. So we don't talk about that in our classes. Like, it's hard enough just to get the computer to print "Hello World" in the first weeks of class. By the end of the class, too, it's not a topic we spend time on. And honestly, this really leads to a conversation about trade-offs. So it is the case that this language called Python generally is slower than a language called C, which we also do explore in Computer Science E-50. The reality, though, is you will spend so much more time, most likely, writing C code than you would Python code. Why? Python's a newer language. It has more features in it. And that is why it's slower, because it's doing more of the heavy lifting for you in accomplishing common goals. But it's expediting your development process. You, the human, are spending more time. Your productivity is higher. You are decreasing the probability of certain types of bugs or mistakes in your code. So those there are trade-offs. And the reality is, too, with most software that people are running, unless you're the Facebooks of the world, the Googles of the world that have thousands of servers where those performance differences really add up, it's not going to move the needle, I think, for most applications to worry about things to that level of detail. Nicely enough, though, it already coincides with cost. Like, the reality is, the faster your application is, the less time it needs to run on the server, which means the more users or customers you can service with that amount of hardware. And so, like, incentives are wonderfully aligned with sustainability, because writing more sustainable code will also decrease your cost. So I do think it's inherent in the process, too, but really only matters at scale. What's Danielle at Proxies in the chat? What's next for you, Professor? What are you working on outside of your CS50 legacy? To be determined. I can say that my colleagues and I, Bernie, who's in one of the tiles here in the window, and I just returned from Indonesia, where we've started doing a lot more teacher outreach post-COVID. We, of course, have made everything very available to students, but in recent years have been focused on building a network of teachers. So we actually led a workshop for about 300 Indonesian middle school and high school teachers that will, in a few weeks' time, go to their own classes and teach introductory computer science. So they spent the past 6 months taking CS50 online, asynchronously, but also synchronously via Zoom, and that was the capstone experience. So I do imagine we'll see more of that as we build up more communities around the world. Other questions or topics?
As someone who's taken the AI one on edX.
Sorry, what was the question, Andra?
It's more of a comment. As someone who has taken the AI version on edX, I noticed that your other professors that you mentored, you've managed to pass your ways on to them. How is that?
It was not deliberate, but yes, I do have a couple of colleagues who have an uncanny knack for mimicking certain speech patterns and or behaviors that I manifest, for better or for worse. But it was not deliberate, per se.
Thank you for your time.
Sure. Danielle asks for someone else in the chat. In your teaching statements, you emphasize the importance of accessibility, irrespective of background. This is obviously something near and dear to many of us at HES. Can you elaborate a bit on how you make CS50 accessible to all students, especially considering the diverse audience? Yeah, so here too, I can rewind to 2007 when I took over the class. And one of the very first things we did was introduce Scratch. I had the fortune, when I was a graduate student, of cross-registering from Harvard at MIT down the road, where Scratch was being developed. And again, someone posted this kindly in the chat. If you haven't seen it, you can go to scratch.mit.edu. We were the first beta testers. And then pretty much a year later, it was released to the real world. And now it's everywhere. But we introduced it into CS50 for college students, for extension school students, for everyone now online, because it really offers, as Mitchell Resnick, the professor behind it, a very low floor. It's very easy for everyone to get on board with coding because it's designed to be so accessible. It's cute, it's playful, it makes nice sounds, but it's real computer science. It's real programming. And so it's not hiding a lot of that detail. It's just getting rid of stuff that was never interesting. Those of you who have programmed before know that a lot of languages have a lot of syntax, textual, parentheses, semicolons, curly braces, and just stupid punctuation that, yes, is necessary to make the darn thing work, but is not at all intellectually interesting. And Scratch gets rid of all of that. And so I think that's partly what I mean by accessibility. We also started changing all of the homework assignments called problem sets in CS50 back in 2007, whereby we tried to repackage computer science fundamentals in just more modern context. We have a problem set nowadays on digital forensics, recovering data, on Instagram-like filters, on encryption and cryptography. At the end of the day, the programs are really the same kinds of programs I was writing myself in school like 20, 30 years ago, but they're just a little trendier and more fun, and it's easier to see the connections to the real world. So that, too, we mean by accessible. And then lastly, non-exhaustively, we also introduced different tracks into the class back in the day for those less comfortable, those more comfortable, and those students somewhere in between. And there's no formal definition of this, but you're more comfortable if you've been programming since you're like 6 years old, but you maybe never had a formal introduction to CS, so you might still take the class. You're less comfortable if you are wondering why you're even in the class. And if you don't know what bucket you're in, you're probably in the middle, somewhere in between by definition. So that too has helped sort of separate the most advanced from the least advanced students, if only to avoid the imposter syndrome that came up earlier, or just the feeling that like everyone else knows more than me, by just bucketizing people in their own more comfortable spaces in sections. And if we missed any questions in the chat, feel free to resurface them. My colleague is kindly helping scroll up and down here. And Danielle, if there's any we missed from prior, happy to answer as well.
I think we hit the major points. We did have a lot of questions about AI and how it would change your the way that you teach and support students, and how CS50 will evolve. But you did touch on that a little bit. I don't know if there's anything else you wanted to add.
Just to say that, frankly, this is a really good time, I think, to be taking computing classes. I mean, even ChatGPT pretty much overnight changed my own methodology for just learning new material, even preparing for classes. It's sort of like Search 2.0 in my mind, where with high probability, it tends to hit the nail right on the head and give you a good, accessible layperson's definition of various topics, even within tech. And I say this is a good time to take a class like CS50 because you really have this virtual duck, this virtual TA available 24/7, 365. And even though the technology is not yet perfect, it is way better than I would have guessed it would be as early as 2024. And this stuff is only going to get better and only get more omnipresent, I'm sure, in other fields as well. And Danielle, I'm not sure if you have a tradition of this, but I do have one other slide I brought. In all of our Zoom-based classes, we have this tradition of, if people want, turning their camera on for a so-called souvenir photo. If Andrew, you wouldn't mind.
I think all set, David.
All done. Thank you so much. Allow me to turn things back over to Danielle.
It's so awkward.
That's great. Thank you so much, really, for your time and for answering so many questions. I saw somebody in the chat said that at almost 60, this is the first time that she's seen an explanation of coding that makes sense. And I, at almost 40, had this same experience when taking your class. So really, thank you just so much for your time, and for being with us today. And yeah, that's all I have. Thank you.
Yeah, thank you all. Nice to connect. Hope to see you in the summer or fall.
Thank you.
Bye-bye.
Bye.